Hello, my name is Engineer Estecklal, inshallah, after this. Basically, I'll be speaking about this part from South Sudan. Basically, just to remind you of what we have talked about so far, you have been reminded by Engineer Remedier about the importance of what the coherent optical link is, and by Engineer Lemit of how the optical coherent link is so important, why we should use it. And we have also been reminded of if we are going to use this, there's going to be challenges. All right. So Bishoy have walked us through the noise, the challenges of the noise, to understand deeper of this. And the next part we'll talk about is we'll look at the channels, the optical fiber channel itself. We have to understand much better about it. So the optical channels, we can classify it into two, and this is based on what we call a normalized frequency, cutoff frequency. So basically, if this normalized frequency is greater than 2.40, we call that a multimode, where we'll have more than one mode going through the fiber channels. And in this multimode, it's utilized in short distances for transmission. And the challenges it have is it have a low bandwidth. The next thing is to couple the light inside the channels. We use the vertical cavity surface emitted laser in the transceiver. Another challenges we have, or the most important we have about this multimode is it has low power, and the cost is so low. That's why it is used in a small scale data center right now in the commercial market. Actually, what we're talking about here is the complexity. Yeah, we don't require more complex. It has no more complexity, easy to implement, has low cost. That's what I mean here. The most important things we'll focus about is the single mode fiber, and that's when the normalized cutoff frequency is less than 2.405. And in this, since it is less, it only have the fundamental mode, only one mode inside the optical fiber. This is a parameter that is called a normalized cutoff frequency, and we determine it using the cutoff wavelengths. We will talk about it in the next slide. It is just a parameter we use to determine to know if we will have more modes or only one mode going through the fiber. So in the single mode, we only have the fundamental, and it is used in the long distance data links. So we can also utilize this in the short distances. It has a higher bandwidth, that's why it has more interest. It used the same vertical cavity surface emitted laser in the transceiver. It has a high power and high cost. And when I talk about the power, I also mean the complexity, the DSP, and all of this part. Now, since we're going to emphasize single mode fiber, we'll need to understand single mode fiber as the channel. And we can look at some property. This is the cutoff wavelength. And the cutoff wavelength is where I have the normalized cutoff frequency, VC, that I was describing here. We can determine it using the core diameter with A and the numerical aperture. So the standard in telecommunication right now is between 1.1 to 1.28 micrometer. And for single mode, as we say. And another important thing, instead of only focusing on the core diameter, we can also look at the mode field diameter. And in this mode field diameter, it guarantees that the optical mode intensity will be greater than 1 over exponential, which is nearly about 13% of the peak value. This diameter is important because it determines the bandwidth and also the transmission distance. We have a spot size. This is the smallest focus we can get from this diameter to transmit the light. We also know in the fiber, the refractive index vary. It's not constant. So we also need to look at a property like the effective. And this effective is the average value we can get. Now, the fundamental mode, which is the linear polarized with the subscript 0,1, this is the fundamental mode. We can approximate it using the Gaussian distribution. as this the gas, and here's our fundamental modes. Now, using these channels, we face more issues when it comes to high data rate. So we'll come to find that the channels right now is giving a nonlinear behavior because we're transmitting a high data rate in the channels. And this nonlinear will only focus on the materials, nonlinearity that happen. And we can see that we have, as the light is propagating inside the channels, there can be a phase shift that can happen inside it, and this can cause a spectral broadening, where as the pulse propagating in the channels, it broadens to a range of a frequency, which can cause interference and all of this. A phase shift can also happen in a cross phase, where we have a two light propagating with a different frequency and propagation. So we can also have a phase shift here. And in this case, it can cause signal distortion and also a crosstalk, because one of these will have asymmetric spectral broadening, where it is bigger than the other one. So in the next part, we'll talk about the linearity. So basically, this is more of a technical part, other than the other part. So after using the matched filter, the far we can get is only cancel the noise, but we have more effects than this. So we need to consider channel mitigations, the effect that happen in the channel. So we have experimented with the two algorithms. We use the adaptive filter, least mean square, and we also use it the RLS. So in this first part, we'll only talk about the least mean square. So basically, the least mean square try to estimate the channels and the noise parameter, and irritatively update and use this estimated parameter to correct the noise and the channel. I'm sorry. I actually mean this estimated parameter, it keep updating iteratively and used to correct the received signal, all right? So it correct this, it continue doing this until our received signal converge. This is where we reach to a minimized value that minimize the error in our signal. The issue we face with least mean square is actually, as we're trying to mitigate the channels, it can enhance the noise as well. And basically what the least mean square do is it try to get the error, and try to get the error using my desired signal and the output after the adaptive filter. So it tried to balance between the channel mitigation and the noise cancellation. So the issue is we have the wedges, we're using the wedges, and after getting the error, we do a convolutions where the noise get enhanced as well. And the LMS actually reached to an optimal solution. However, it takes longer to converge.